Okay, so let's start our second sub-lecture and start to get into the details of these metamorphic rocks that we're going to need to know and how they're related to compositional and texture terms. The metamorphic grade. When we're talking about the metamorphic grade of a metamorphic rock, we really just mean how metamorphosed is it? How much heat, how much pressure has it been subjected to over its lifetime? And we can describe it as low grade or high grade or medium grade or intermediate grade in the middle there. And those reflect changes in both the pressure and the temperature of those rocks. Low grade metamorphic rocks will form somewhere up here, right? So low pressure, low temperature. High grade metamorphic rocks, you're increasing the pressure because you're going down the y-axis. You're increasing the temperature because you're going to the right on the x-axis here. So the rocks down here are at higher pressure and higher temperature. So these are high grade rocks. And in between, these are medium grade. In this area over here, you generally don't form metamorphic rocks because it's really hard for you to increase the pressure this much without also increasing the temperature. Just by virtue of, if we are going to squish these rocks together and they're going to be deep enough that metamorphism is going to happen with all this pressure, then we probably are increasing the temperature a little bit as well. So, metamorphic grade, we can tell by looking at the minerals in a rock, and that is because different minerals in metamorphic rocks form under different conditions. So low-grade metamorphic rocks will have different minerals than high-grade metamorphic rocks. That means that we can use the minerals in a metamorphic rock to work backwards and determine what the temperature and the pressure were. Put in a fancy way, we can use the minerals as a geobarometer. Barometers measure pressure. So this is like an earth pressure barometer. And a geothermometer means this is sort of an earth temperature measuring device. Simply by reading the minerals in a rock, we can know the pressure and temperature under which those minerals formed. That is, if we're looking at a metamorphic rock. Some of the rocks that we'll talk about might be slate and phyllite and schist and gneiss. And eventually we get into a partially igneous rock called a migmatite. And we're going to learn more about these 4 types of rocks here. And I'm going to write them out because they're all spelled just a little bit weird. Here's another view of what I mean by different minerals forming in these different rocks under different conditions. So diagenesis is what we call processes that are lower temperature even than metamorphism happens. But then we have low, intermediate, or medium, and high grades. Same sort of diagram over here, low, intermediate, and high grade metamorphism. And what the chart says is the minerals that are present at each of those conditions. What's the difference between these 2 charts? This one starts out as shale, one of our sedimentary rocks with tiny little particles, right? And this one is if we were to take a mafic igneous rock like basalt and we metamorphose it. Different minerals are going to form from each of those starting materials, but they have some things in common. For example, a mineral called chlorite might form under low-grade conditions in both of these rocks. A mineral called garnet might form in intermediate conditions in both of these rocks. And then there are some minerals that only form in one. So in shale, you might get minerals like kyanite or sillimanite forming. In mafic rocks, you'll actually start to form some new pyroxenes. Those are minerals like augite. We've talked about augite before when talking about igneous rocks. Now, I'm not going to expect you to memorize these because we haven't looked at most of these minerals, right? We've looked at muscovite and we've looked at biotite, but for the most part, we haven't seen these minerals before. We've also looked at plagioclase. I'm not going to ask you to memorize this chart, but I may ask you to interpret a chart like this and say, if I said you have a rock that's got both biotite and kyanite in it, what rock did it start out as and what metamorphic grade did it form under? You would look at this chart and you'd try to find where biotite and kyanite are both in the same rock. So, okay, here's biotite, could be anywhere in here, and here's kyanite. And the places in which those overlap are this region here. So it's got to be an intermediate rock and it probably started out as a shale. We can learn that based on one of these charts that geologists have put together simply by reading the minerals that are in a rock. That's the point of looking at this here. When I use the term parent rock, I'm referring to the rock type which a rock started out as before it got metamorphosed. So the parent existed first, and then it became the child rock, which is kind of a weird way to think about it, but the term parent rock means the original rock type for a metamorphic rock. So under heat and pressure, the minerals in one of these parent rocks will recrystallize and they will form new minerals. Oftentimes those minerals will also be larger grains than what the parent rock started out as. So we're not only looking for new minerals like we've been talking about, but we're also going to form larger mineral crystals as well. When you have more heat and pressure, you get larger metamorphic mineral grains. So that's going to be important, and that suggests to us that there's going to be some texture that we can think about based on the metamorphic grade of rocks. So keep that in mind too. We're going to start out with shale. Shale is not a metamorphic rock. Shale is a sedimentary rock. Should be able to tell me its texture and composition, at least on some level. So it's clastic. It's not formed from chemical precipitates. It's got very fine particles, mostly clay-sized particles. And those have arranged themselves in flat-lying layers, which is why shale breaks so easily into these flat chips. It's got fissility. We've learned all that already if you've been doing the sedimentary lectures. If we take a shale like this and we metamorphose it, then we can say that shale is the parent of the next rock. So under low grades, it will form a rock called slate. It can be hard to tell shale and slate apart. You can't see the grains in any of them, right? So these are still very fine grains, too fine to see. But the rock overall is harder to break. It's sort of been baked a little bit. So if it breaks into chips, it's probably still shale. But it's much more difficult to break, or it breaks into more chunky pieces, it's probably slate. Right, so slate, you're probably used to. Some old tile roofs will have slate tiles. Sometimes you'll have slate as stepping stones. It often gets used in landscaping in that way. And it also makes up chalkboards. For those of you that ever still had chalkboards in your classrooms, a lot of those are made of natural slate. So to remember, slate itself, its parent rock was shale. But we could talk about slate being the parent rock of the next sort of low to intermediate grade rock, which is called phyllite. So this is pronounced phyllite. What's going on in this rock? We still can't see the grains, but they are getting bigger. And we've changed the minerals in them so that instead of sort of dull minerals, we start to get a little shiny. So the rock looks waxy, reflects light just a little bit. And that's because it has tiny little mica grains in it, too small to see with your naked eye, but the overall effect of them is that it makes the rock sort of shiny. So it looks shiny, and it also starts to look just a little bit wavy. So that's how we could tell slate apart from phyllite, is the appearance of this sort of shiny, lustrous appearance, and it will start to look wavier. You still can't see the grains though. Once you can see the grains, if you metamorphose that a little more, so this is intermediate to high grade metamorphism, you have a rock called schist. These grains will still be small, but you can pick individual grains out with your naked eye. It will be very sparkly, and it will look like a lot of these grains are sort of flat sheet-shaped grains here for the most part. Right, there's some in there, et cetera, et cetera. A lot of this that you're seeing is mica. You'll have some sort of reddish grains often mixed in that are garnets, maybe. But these you can see with your naked eye, and it's got a sparkly appearance. So that's schist. Then that itself, if you metamorphose that all the way to a high-grade metamorphic rock, you get that first rock that we saw on the very first slide, which is called gneiss. It's got bands of light and dark minerals. A lot of these minerals are going to be similar to the minerals that you found in igneous rocks. So there's probably some feldspar in here. There's probably some biotite and amphibole in here. Some amphibole, right, like hornblende. You've seen that word before, certainly. And you can really easily see the difference in between the light and the dark sections in this rock because the crystal grains are large enough to see with your naked eye still. Here's another picture of a really cool outcrop of gneiss where all of the bands are oriented in the same direction. And you can really clearly see from all the way back here that they're alternating light and dark bands of minerals. They're not always the same thickness. Some bands are very thick, some are thin. But if you see white and black banding in a metamorphic rock, that's a gneiss. So these rocks that we've looked at, slate, phyllite, schist, and gneiss, all have a particular texture that we want to talk about. And that texture we call foliation. We say all of these four rocks are foliated, which means that there's layering to them. Either those rocks are layered like slate in that they have sort of these parallel cleavage planes of the minerals, and so it's still a little bit chippy in the same way that shale forms chips, right, or flat layers. Or in some cases, you can see banding like you see in gneiss. But in all four of these cases, slate, phyllite, schist, and gneiss, you can see apparent layering. And in metamorphic rocks, we call that foliation. Now, why are these rocks able to form some layering, some foliation to them? There's two reasons that they have foliation. One is that they contain minerals which are longer in one direction than another. So that means that they can align. If everything, was the same size in every direction, like cubes or spheres, you really can't form layers of those. At least the layering won't be very apparent. And that's because there's no way for them to orient. So that's not what we mean. We mean either they've got sheet-shaped minerals like the mica, right, where it's very skinny little shapes, but they're longer in this direction than they are in this direction. Or you can have some sort of needle-shaped crystals. Right, my art skills are really coming into play here, but we've got it, it's much longer that way than it is in either of these other two directions. So in order to form foliation, you need minerals which are longer in one direction than another. That allows them to form layers. The other thing that they need is they need to form under some directed pressure. So it can't just be that rocks are sort of sitting on top of you, which puts pressure in every direction. But instead, you might form somewhere like at a convergent boundary, as we'll learn in plate tectonics, or maybe as you've already learned. These are places where one plate is pushing into another plate. And that pushing, the rocks in the middle here are being squished in a particular direction. That squishing in a certain direction causes compression in that direction, and it causes the minerals to align perpendicularly to that. So it helps promote that foliation because the directed squishing forms, the directed squishing causes directionality to the pressure being exerted on the rock. So if we write all these out, we had our slate, our phyllite, our schist, and our gneiss, and we have a little cartoon of how the crystal size increases. So higher grade means larger crystals. That's one element of the texture. The other element for these 4 rocks is that they're foliated. And we go from very fine foliations in the slate and the phyllite to schist and gneiss, where those foliations are much more visible, to the point that you get really visible light and dark banding. We didn't talk about a migmatite, and that's because this is sort of a hybrid of metamorphic and igneous, because a few of the minerals have started to melt in here, but not all. So what do you call it then? Well, you probably call it a little bit metamorphic and a little bit igneous. We won't talk about migmatites too much. We'll keep it simple in here. You will see slate, phyllite, schist, and gneiss again. There are a couple of rocks that we will learn that are non-foliated. If you were to metamorphose sandstone, even sandstone that has some banding to it, that seems to have beds in it, and you metamorphose it and you put directed pressure on it, you're still going to get a non-foliated rock. And that's because what we can call equigranular, the grains in there they tend to be pretty close to spherical, right? So they're the same size in every direction. It's really difficult to get foliation when the grains are the same size in every direction. So that sandstone is going to turn into a quartzite that really has no apparent layering. But what quartzite will do is it will have almost all quartz in it. It'll have sort of a sugary appearance, where, like, if you've ever seen a block of sugar that's been wet a little bit and then it's sort of dried out and it's all sort of stuck together, that's kind of what this rock will give you the appearance of. Quartzite is a metamorphic rock that's made mostly of quartz. It can form at low, intermediate, or high grades. It usually starts as a sandstone, and it doesn't have any foliation to it. Limestone. Limestone is our only rock that we've looked at in this metamorphic section that's not mostly made of silicate. So remember that limestone is largely calcite, which is calcium carbonate, and it fizzes. When it becomes marble, it stays as calcite. Marble itself also fizzes because it's also made of calcite, calcium carbonate. But those calcite grains are roughly the same size in every direction, so that it tends to be pretty non-foliated. You might see some, wormy looking weird layers to it, but for the most part, the bulk of this rock, you don't see any layering, no foliation in this part here. So we tend to think of marble as a metamorphic rock that is non-foliated. It too can form at low, intermediate, or high grades, and it's starts out as limestone. So limestone is the parent rock of marble. So remember, not all metamorphism creates foliated textures. The 2 reasons that you might have foliation absent are if you have a rock that hasn't had any differential stress, right? It hasn't been squished in one direction. If you haven't been squished in one direction, you're going to stay a non-foliated rock. Or you've got a rock where all the minerals are equal sizes in all directions, and that's the case for quartzite and marble. What would happen if you took a rock like shale and you subjected it to metamorphism, but you didn't have that directed pressure? You would form a rock called hornfells, and we're just not going to worry about that. Hornfells are hard to tell apart. They're low, intermediate, or high grade. They don't have very visible crystals. It can be really hard to look at. So for the most part, we're going to focus on those 6 metamorphic rocks. Let's break this down and just talk about texture and composition all in one spot. For the most part, these metamorphic rocks that we've looked at are all silicate based. So the only one that's not is marble. To check the composition, you can simply say, does it fizz? At least for our purposes. If it does fizz, it's marble. If not, it's made of silicate. Any kind of silicate minerals, right? So it could be micas, could be quartz, could be a bunch of other things. The next thing to check is, does it have what we call schistosity, shininess aligned along cleavage planes? If yes, it contains those aligned mica particles, and it could be the phyllite, where you don't see the crystals, but it's still sort of waxy shiny. Or it could be schist, if you do see the crystals. The texture that we're going to think about, well, one part that I don't have written here is foliation. That's a big part of texture. But the other thing is going to be how big are the crystals that you see. If it's not marble and it's not quartzite and the crystals are too small to see, it's either slate or phyllite. And you can tell them apart by looking for that shininess. If the crystals are big enough to see, it's either schist or gneiss. And you're going to decide, is it light and dark banded, or is it shiny with specks of mica in it? And that's how you tell gneiss apart from schist.